Can you lower the microphone?
Sorry, I forgot I'm short. I'm Rupal. I'm a PhD student at the University of Illinois, Urbana-Champaign, and I will be talking about a paper on zero-shot coordination and ad hoc teams with generalized policy improvement and different surveys. Lots of words, and I'll hopefully break it down in an understandable way. Okay, so setting out some of the background goal and motivation. So we're looking at ad hoc teaming here to define that. So it's a key challenge for multi-agent teams where there's a single autonomous agent, and we want this agent to successfully coordinate with other unknown teammates. So beforehand, we don't know what type of teammates are going to be on our team. Specifically for ad hoc teaming, we're looking at with this paper at zero-shot coordination. So that's how to use prior knowledge to successfully coordinate with these unknown teammates without any online inference or learning during the situation with a new teammate. So as a motivating scenario, maybe you can consider a search and rescue mission where there's robots and maybe also field agents and people are deployed from different organizations. And so these robots and people might have different strategies, and the robots might have different capabilities in terms of being able to solve different tasks on the field. And maybe beforehand, for our ego autonomous agent, we've had the opportunity to experience some of these different strategies and capabilities. But beforehand, when we're in this kind of dynamic and complex environment, we don't know exactly who else will be there working with us. So a brief overview of prior work in ad hoc teams. This first category we'll call type-based methods. So what these methods will do is we'll train the ego or learner agent with a predefined kind of number of teammates. So we're going to learn a pre-trained library of policies for each of those teammates. And then when we encounter a new teammate, we're going to infer the behavior with some online samples. And based on that inference step, we can then choose a best response, basically, from that library. The second kind of category of methods we'll call robust methods. So the challenge that these methods are addressing is how can we generate a truly diverse training pool of teammates to train with? And then what we do is we're going to train a single robust policy. So a policy that's robust to these different types of diverse strategies. And then kind of in contrast and kind of, but also related to both of these methods. So what our objective of this paper is to dynamically leverage this entire pre-trained library for truly zero-shot coordination. So we do this with two key ideas in our algorithm, and I'll walk through both of them. So the first one is called Generalized Policy Improvement, or GPI. So to be able to use GPI for our learner teammates, we have to do some set up some stuff in the background. So we linearize our rewards using a predefined set of features, so phi, and these are weighted with a vector, so that's W. And then for a policy, what we can do is if we compute the expected discounted sum of rewards, that's known as psi. And these are in the literature known as successor features. What's really cool is you can then show theoretically that the action value function Q is equivalent to psi times W. So you kind of decouple the action value function into this quantity of psi and W. So now we can use the GPI policy to dynamically leverage the entire library of pre-trained policies. Why can we do that is because we have decoupled Q into psi times W, and because we're doing cooperative ad hoc teaming, this W stays the same throughout because we have a shared team reward that's the same and we're considering the same situation. What's changing in ad hoc teaming is the teammate, not the reward. But there is one more caveat, because we have these different teammates, so differing from the original successor feature and other GPI work out there for single agents, because we have other teammates, these teammates with their different strategies are inducing different dynamics onto the MDP, so from a theoretical standpoint. So technically, all these psis that we have learned from our pre-training step are no longer valid when we're working with a new teammate. So to kind of address that, we introduced difference rewards. So difference rewards is in multi-agent reinforcement learning now a pretty commonly used aspect. So we're taking this idea of difference rewards and using that to address this change in dynamics in adult teaming. So difference rewards address the multi-agent credit assignment problem, and some of the previous speakers have also talked about this. So, but as a brief overview, what it is basically is it's a counterfactual kind of argument. So if you look at the equation, you can see that we have the team reward, and we're also computing the expected reward for this for a single agent's perspective. What if I took all of these other actions? What would the reward be? And so our idea is to let GPI operate with action value functions, kind of evaluated with respect to the learner's difference rewards. So theoretically, we can still not guarantee policy improvement because we're still using the teammate dynamics from pre-training. But where our hypothesis is and what we can show in results is that evaluating with respect to these difference rewards does reduce the impact of that distribution shift. And to kind of give an illustrative example of how this is working on difference rewards from a learner's perspective. So the environment I've shown here is a cooperative foraging environment where all the circles are different types of objects or fruits that the team has to collect. Our agents are triangles. The learner ego agent is in green and the teammate is purple. So on the left-hand side, here's a situation where the teammate is doing the action, so go to the right to collect the thing, and that is what is giving the team the reward. And from the computations that are displayed next to the image are from the learner's perspective, so the learner's difference rewards. So the learner is looking at if I took any other action, what would happen? The team is still getting the reward, and so if you see in the computation delta R, that's reflected. The reward is, difference reward for the learner is 0. So the learner's action now knows I did not contribute to getting the reward. And you contrast that to the situation on the right where the learner is doing the action that gets the reward. And then if we go through the computation of the difference reward, we can see it's non-zero. So the learner knows that the action that I took in this scenario was actually useful to getting the reward. So now we're going to put all these little pieces together. So step 1, we have a pre-training phase. So we're going to optimize the learner policy for each of these, we call them source adult teams, so these teammates. We use true learning in our work. And then after that, we do offline policy evaluation for each of those action value functions. And we're doing that evaluation with respect to the difference rewards that we just talked about. And then finally, in step 3, when we encounter a new teammate, we apply this GPI policy for truly zero-shot coordination. So going back to this foraging environment that I've introduced earlier, we also in the paper do some extensive evolution studies, but I'll point out one that's particularly interesting here. So kind of really nailing down and emphasizing why doing this step with evaluating with respect to the difference rewards for the learner is really important. So kind of left to right, we have the positions of the objects in the environment, so it's frozen at this state. And what we're displaying in these heat maps is the normalized value of the learner being in each of the states. Okay, so first we have the oracle, so we're using this as the baseline as what would be the truly accurate values if we did have unlimited training time with a new teammate. So we're using that as our baseline. The next image is GPAT without doing that difference reward evaluation. So we can see that we have a much higher error. On average, averaged out to about 32% error in the values, and most of these overestimated values are in the top right where the yellow objects are. And that's important because in this scenario, that's what the new teammate is going to collect. So, and then if we do evaluate with respect to difference rewards, we see that go down a little to 18%. So just in summary, that doing this evaluation step is pretty important because it results in more aligned values. And that's important for the GPI policy because that's how we're dynamically switching between policies in the library is by comparing these values. So within foraging itself, we look at 3 different experiments, and these are designed to have different levels of difficulty from the library, and in terms of relevance to coordinating with the new teammate itself. So the first two are GPAT performs our baselines and is using all free train policies very effectively. The third case here is an extreme case, so we're saying what if our teammates are not related at all to the new teammate that we're going to see? So we haven't learned anything. The learner hasn't learned anything useful in the free training step. And kind of as expected, we see that our method does struggle there. We also do experiments in predator-prey and overcooked. So in predator-prey, the results are showing that GPAT can coordinate well with multiple teammates. So we have more than just one other teammate. And we're also coordinating in an environment that has changing other dynamics that are changing. So basically the prey that are moving around. And then in overcooked, we actually see a larger improvement in performance between GPAT and the baselines. So that kind of indicates that GPAT can scale to a more complex scenario, and perhaps it's more effective than alternatives for these increasingly complex tasks. And there's different subtasks that are overlapping and have different time interdependencies. Just to summarize, we introduced a GPAT novel algorithm that uses generalized policy improvement and difference rewards for zero-shot coordination. And we're doing that by leveraging an entire library of pre-trained policies and dynamically switching through them. And we're addressing this shift in dynamics through difference rewards that are induced by the new teammates. In the future, we're interested in looking theoretically analyzing this method, considering adapting online to the new teammate, and also considering partial observability. We also did a multi-robot demonstration. I'll kind of let that play in the background, maybe during questions. I'd like to acknowledge my collaborators and funding agencies. And thank you all for your attention. You can now get coffee, and I'll be happy to answer any questions.
Thanks for the talk. Hello. Hey. Thanks for the talk. How, I guess, did you implement the different rules? Because sometimes it can be like a little tricky. Like, do you create like a copy of the environment, or?
Yes. So we are assuming that we have access to. Practically, we're not creating many different environments, but we're assuming we have access to something that lets us do that counterfactual computation. Yeah.
Okay, and then that was easy to do, to create a copy, because sometimes I guess if the environment is noisy.
Yeah, so we have, so we're taking, there's a fixed state, so at each time step, right, the state is fixed, we know where the agents and objects are, and we're just asking this like simulator, if the learner took this other action, what would happen? So, maybe it's like memory-wise, probably a little heavy computationally on the back-end side.
Okay, and there's no like randomness in the simulator, because sometimes even if you pass the same state, you still just have simulators.
Yeah, we don't have, these environments are not like stochastic in that sense.
Okay.
Yeah, we have not, that makes sense, yeah.
Okay, thanks. I think we're running late. Thanks everybody for attending.